Good
evening. Welcome to the February meeting of the Baton Rouge Astronomical Society. Tonight, we're going to be talking about radio astronomy, and I am the speaker for tonight. So, without any further ado on it, we'll get started on it. We have a lot of information here I have from Sarah, the Society for Amateur Radio Astronomers, and also from the National Radio Astronomy Observatory. Okay. So, let's see here. Which one of these does it? Here we go.
Hold on.
Okay.
Try it again. Here, bring it over.
Which button?
Here, let me see.
Wait, one moment here. I have trouble with the thing to advance it here. Which one is it?
It's just the right and left up there.
Okay, gotcha.
If it's not the right one, it's the left.
Okay. There we go.
Well, don't press that one.
What happened here now? There we go. All right, then let's try this one more time here.
John, quit pressing buttons.
Okay. As always, technical difficulties.
All right, let me see.
Try one more time here.
Don't press this button. That apparently starts the thing over and disconnects it. So press either this button or this button.
That's what I was.
Not this one or this one. All right. Let's see. And I've got the wrong thing.
Okay, you got it there or not?
All right. All right. Try it now. There you go.
There we go.
Don't press the middle button, John.
I
I
won't.
swear.
All right.
He will smite me.
And I do not want to be smoked. Okay, radio is part of the electromagnetic spectrum along with light. We're all familiar with light. But radio is also part of the electromagnetic spectrum. This is an idea of what the radio electromagnetic spectrum is. You have radio down in the lower section in here. Then you have microwaves. We move up to infrared, which is getting larger waveforms. And then you have the visible light in the middle of it. And then you go to ultraviolet, X-rays, and gamma rays. And they show you the different ones in here. Whenever electric charge changes speed or direction, it gives off an electromagnetic wave. And how fast the wave does its wiggling is determine what kind of electromagnetic radiation it is, and also it also is the frequency of it. Now this is a chart of the entire electromagnetic spectrum. The electromagnetic spectrum can be placed in order from the lowest energy to highest energy. Starting with lowest is radio, infrared, visible light, ultraviolet, X-rays, and gamma rays is the highest energy. And, you know, some things we have what's called the FRBs, fast radio bursts that astronomers do, and we have gamma ray bursts that we look at and stuff. A lot of our satellites look at things like that. But this gives you an idea of how much energy, and the energy of a photon is measured in electron volts. And then the frequency is like what we say, the 60 hertz AC. Well, that's the frequency is 60 times a minute. Sorry, a second, isn't it? But anyway, hertz is the frequency on it. So then you have different sources, size of the wavelength in meters. We normally talk about it in meter things, or the wavelengths for radio and that way. Come on now.
flip the power switch off and then back on.
Yep. There you go. That's the way we have a wire. I didn't do it. There we go. That was the wrong way. Still not doing anything here.
Right.
Can Ben just manually fix this
There we
house?
go.
Yeah, I'll just manually do it. That's fine.
Okay. Now, the electrical signals versus sound, what is the difference between the two? Sound is longitudinal, while light is transverse. The sound traveling at about 1,100 foot a second, that's why when you hear a thunderbolt or something like that, you can count like 1,001, 1,002. For every 4 seconds like that, you count, it's about a mile away from you. Okay, so light travels at about 186,000 miles per second. Now, sound travels only in matter. Air is matter, things, but there's no hardly any matter in space, so sound doesn't travel in space itself. While light can travel through the vacuum, through almost any medium other than solids. And sound is a vibrating matter, while light is vibrating energy. Okay? You know, okay. Now, with the spectrum of objects that you can see with it, as the picture shows here, you saw many objects can be viewed better in different types of electromagnetic radiation. And remember, the higher up the picture you go, the more energetic the object has to be. Therefore, cooler objects will be near the bottom, while really hot objects will be near the top. So what do you have in there? You got infrared. Okay? Infrared is like interstellar dust clouds, is what we can see. Okay? Above that there, you got the visible light. We can see galaxies, stars, the solar spectrum. This is what we see in our telescopes. Okay? Then you go to ultraviolet, which would be solar flares. And what's that? Very young star there, like that, I believe it is. And ultraviolet, we have a couple of satellites up that can see in the ultraviolet. And then you go to gamma rays and X-rays, where you have pulsars, hot interstellar gas, black holes, supernovas, gas jets, solar flares, etc., like this. And we have different satellites up to see all of that stuff too. Okay, Scott. Okay, now the electromagnetic spectrum and radio. Radio signals are able to reach Earth, and we have so many large radio observatories. The big one we have is a Green Bank, and we also have the NRAO one. There's 2 main ones we have. There's a big one in Australia. I don't blank on the name of it right now. But these are also the ones that NASA uses for communications with probes. Like right now, the Voyager 1, I think it is there, that's about the furthest distance of anything man-made. It takes hours to get to it, and the signal is so small, it's unbelievable, but it still answers, which is interesting. Anyway, yeah, many large radio observatories have been built to look at objects through this large portion of the electromagnetic spectrum. The pictures are showing the Milky Way galaxy in a 360-degree, this is the one on the lower right, view in both visible light. At the top, you see the smear across there, and then radio radiation, the bottom one, and that radio radiation is at 408 megahertz frequency. Remember, the radio radiation allows us to look at objects in relatively low energy. It includes dust and gases in the galaxy and solar system. Well, visible dust can obscure a lot of things on us. But with radio frequencies, we can see through the dust. And that's how we're able to see stuff that's been clouded over with dust that we cannot see with our telescopes by using radio. Scott? Okay. Now, the electromagnetic spectrum in the infrared, The infrared radiation is the next band of radiation above radio frequencies. So what we associate with heat, like the heat lamps we use to keep food warm in our fast food places, and you can say tanning to a degree. The top picture shows that the heat picture of several houses, and the bright colors are large heat leaking out of the areas. And note the windows are the ones that you really see it bright on there. And the bottom picture shows that what a bee might be compared to our vision of a flower. The flower you see there, the yellow and the blue there is what a bee would see with infrared. Right, Scott? Okay, so still in infrared here, the two pictures that's right. The two pictures show the Milky Way in visible light at the top, which we saw earlier, and then the infrared radiation used to view moderately warm objects. You can see the galaxy clearly in both pictures, but using the IR image, we can now see the dust in the solar system, with the S-shaped pink curve in the bottom picture. That's the dust in our solar system. Okay, this allows astronomers to see dust and gas that is invisible to our eyes in optical telescopes. Scott? Okay, now we go into the ultraviolet. After we have the infrared, we go into the visible, then we go just past visible is ultraviolet. So remember, the visible light comes after the IR, and UV comes after visible light. This picture shows features of Jupiter in both visible light on the top and ultraviolet on the bottom. The auroras on Jupiter are only seen using UV pictures because they are created by highly energetic particles being drawn to the poles by the magnetic field of Jupiter or any other planet, including Earth. Ours is magnetic poles that involved with the Van Allen radiation belts on ours. But you can see there the UV pictures there, and you can see like on the bottom of there, Jupiter's auroras around the poles. That can be seen in the UV. That we do not see it in regular visible light that we see with our telescopes. Scott? Okay then. Ultraviolet radiation shows objects that are fairly energetic. This is a picture of M74 galaxy, and we see the distribution of energy particles and gases, the things we cannot see as well in visible light. You would see normally just the dotted stars and maybe or something like that invisible, but under ultraviolet you can see a lot more. Stop. And after the ultraviolet, we get into X-rays. Pictures show that the sun, at the same time, but in different bands of electromagnetic radiation. The top picture is visible light. It shows the surface of the sun called the photosphere. The middle picture was taken using the hydrogen alpha filter, looking only at the light coming from the sun due to one form of hydrogen, which is in the red part of our visible spectrum. It shows the atmosphere of the sun called the chromosphere. And that's what we use a lot for our filters that we do when we do solar viewing. We look at hydrogen alpha in that light. The final picture is taken in X-rays, showing the very energetic regions of the sun where it's putting out X-rays. Now I just want to mention that the SOHO satellite gives you different bands by way of hydrogen alpha, but they also do calcium. They do quite a few different elements and stuff. So you see a lot of different views on that through the SOHO telescope. Scott? X-rays too, the two pictures, of course, again, the Milky Way in visible light, and then the X-rays on the bottom, which is very hot objects. You can see that clearly in both pictures use the X-ray. We can see the very energetic objects that are invisible to our eyes. Because if you look on the bottom there, what you see on the bottom is not what you see on the upper one. The upper one is what we visually see like through our telescopes. You know that not all of them are within the plane of the galaxy, because you got a couple of spots above the plane of our galaxy that you can see in the X-ray. Scott?
Well,
I want to do it, that's Scott.
It's just behaving badly.
There we go. Then after the X-rays, we get into the gamma rays, which are some of the higher frequencies there. These two pictures again, visible, there. The gamma ray radiation is used for most energetic of objects. You can see it clearly in both the pictures, but with the gamma ray image on the lower one, we now see the most energetic objects in our part of the universe, which are normally invisible to our eyes, and optical telescopes. And then again, not all of the objects are within the plane of our galaxy. Do you see the difference in there for the gamma rays versus visible, which is what we always see in our telescopes? Okay, now this is just the different wavelengths, what the Milky Way would look like. We talk about atomic hydrogen, which is called the hydrogen line, radio, 2.7 gigahertz, molecular hydrogen, infrared, mid-infrared, near-infrared, the optical, you can see our Milky Way there across the band for optical, then the X-ray, and then gamma rays on there. Okay, Scott? And why radio, and what causes the radio emissions? Why do astronomers use radio telescopes? Well, first of all, we can see the higher frequencies and stuff like that too, and also it sees through dust. What causes radio emissions we observe with radio telescopes? That's a big question. Next one, Scott. Okay. These are the frequencies available from Earth. In other words, our radio telescopes on Earth, not those that are up in space. You can see the gamma rays, X-rays, ultraviolet light are blocked by our upper atmosphere. That's why we have to use satellites to see it with. Okay, then most of what we can see is visible light observable from Earth with some atmospheric distortion, which is this portion right here. And then we have most of the infrared spectrum absorbed by the atmospheric gases, which are best observed from space, also through infrared. Then we have radio waves, which are observable from Earth. Then we have long wavelength radio waves that are blocked. So that gives you an idea of the frequency of it, like a 0.1 nanometers to 1 nanometer, 100 nanometers, you get up to 1 micrometer, you get all the way up to 1 millimeter, and all the way down over there to 1 kilometer in length for the frequency and the waveform.
Why are the long ones blocked?
Trying to remember that, Tom.
It just seems.
What is it? Because I think it's the troposphere, I think it is. They're so long that they don't bounce, they don't get, they don't, this, well, for 1 kilometer long, yeah. You don't get the skip, you don't get the bounce off of it. The ionosphere, not troposphere, the ionosphere. You're not getting the bounce you need for it. That's why the real long ones are blocked. And of course, a lot longer than that will be gravity waves, which is what LIGO does. Scott. Okay, then as you can see there, from the side, only light and radio are readily available from our surface. And a few of the lower infrared is also available there, what's called near infrared. And if you want to observe from the surface, you need an optical or a radio telescope, because you can't see any of the other frequencies on the surface of the planet. Also note that radio offers at least 100 times more observable wavelengths than optical does, because optical is such a small area for optical versus all our other wavelengths. Okay, now we have different instruments across the spectrum. What do they use to observe objects at various frequencies? Okay, this is like an optical one. This is like a, looks like it's a refractor there, a Keplerian one it says. And you see there the general idea of how one is built. Of course, the example of the real big one there, the objective lens and how the light is focused into the eyepiece. So that's the refractor. Next one, Scott. Now the reflector here is like the Newtonians, like our Dobsonians, like their Newtonians. And this gives you a diagram here of how it is built in the picture of them like that. That's a reflector. Next one, Scott. Then we have multi-mirror one. As you can see here, multi-mirrors like this are some of the big telescopes we have, especially some of that like out in Hawaii and a few of them, I believe, down in Chile also that way there. And also multi-mirror is the James Webb one, but that's in space. Next, Scott. And then you have another optical, which is a space-based one, which is Hubble, which has, by the way, been up there 22, 23 years, if I remember correctly. Next, Scott. And then you have a radio telescope, Arecibo. This was made before the accident, and they'll see what this picture was here. By the way, the latest word in it is that they are not going to even make an attempt to rebuild it or do anything. It's going to be scrapped. And a lot of people aren't too happy about it. The National Science Foundation who runs it says it's just too expensive. They cannot afford to do it. Next up. Okay, this is the what's called the Very Long Array. And this is, as you can see, the radio dishes here, that's in like a Y shape up there, but they can move them in all different shapes and configurations, from real long for interferometry and big baseline to combine them together to get higher resolution. They can put them in all types of configurations on VLA, and that, if I remember right, that's out in Arizona, if I remember correctly.
Oh, Mexico.
New Mexico, I'm sorry, New Mexico. Yeah, because you went saw it, didn't you?
Yeah, I was there.
Okay. Next one, Scott. Okay, then you have the NRAO and the Green Bank. That's the big ones there that they use. That's the big radio telescopes that are used there. Next, Scott. And then we have the ones in space. We've got the Chandra for X-rays. We've got the IRAS. The WMAP extender like this. IRAS, I believe, is infrared. Anyway, the imaging of radio versus optical. What do the images each look like? Your optical imaging shows you there. The images taken on modern optical telescopes use charge-coupled devices, which is digital cameras, which uses millions of pixels to represent the data, and the photodiodes collect light and energy, convert them into voltages, which they download row by row, etc. And the columns to maintain their positional information, allow the reconstruction of what it sees. Okay, and then we go, pixels are obvious in the image below. You can see the pixels on the right there. One optical image contains millions of pixels, all captured at the exact same time. By the way, the Vera Rubin is going to be something like 100 and some odd million pixels, I believe, that camera that they go for. It's the largest one built ever. Anyways, there are some examples of digital astronomy that you see. And a lot of stuff there, what we do is digital is what we do for astrophotography, because you use cameras for that there, the pixels and stuff. So you have that. Okay, then radio imaging. Example, some examples there. You see the Eagle Nebula, solar flares, M51 galaxy, M13 globular, etc. So next one, Scott. And radio telescopes can only collect one pixel at a time. Each radio image is a composite of many data collections, and each image takes hours, days, or even years. A full sky image of an amateur's backyard sky could take years. So a lot of these radio ones there, that's why, like last year when they did the image, the black hole, I believe it was M81, was it they did it on? Was it M81? Okay, but when they did that, they had radio telescopes all the way across the globe, about 8 to 10 of them all together, and they tied them together for synchronizing timing to do a large interferometry line to get the resolution. Without it, one from like one edge of the globe to the other as it's facing toward it, you could not get the resolution to be able to do that. That's why some of the larger telescopes are built right now. I think one of them is about to be built out in Hawaii. It's going to be a big help on it for doing stuff like this in interferometry. Okay, then, let me see here. Okay, radio telescopes are better resolved, better because you can simulate much larger radio telescopes by linking many, as I said, here together. And the effective size is based on the diameter of the farthest link. So if you got one on one side of the Earth and one on the other side, which is about, I know it's 72,000 miles around, so it's 3,000 or 4,000 miles anyway, between the two of them. That's like having a telescope that big and that wide. Do the interferometry and the stuff of their definition they can do on it. That's why we're able to get that picture of that black hole. Because otherwise it's too small and too far away, we wouldn't be able to get it. Okay, next one. Okay, an example of now this is a sample of an amateur radio telescope showing a 24-hour drift scan made up of thousands of pixels with one pixel every 10 seconds. It's called integration time. And this is like the amateur radio telescope here. It's Sagittarius A, which is the center of our galaxy. That's an example of what it would look like for a 24-hour scan. Next. Okay. And when you have enough single charts collected together, they combine to get a multiple chart, such as this one here, which also is from amateur radio astronomer. So you can see the lines there in the different times and stuff. Stop. When all the charts put together, they can be assembled into an image, and that's the same data as the image form, using black and red, black for low intensity and red for the high intensity. So it's like almost like a 3D picture of what the radio telescope is seeing. Stop. In the professional ones, you can see the neutral gas disk of the Milky Way. You can see radio quasars. You can see radio galaxies. There's the galactic center up there. You see atomic hydrogen and M81. You see quite a few different things in the big professional ones. Next up. Okay, and then this. Whoops.
Doing good.
Okay, I guess that's it. They're showing you the expansion on it like that to show you something like what they're showing, like the one over on the side there. These are the Sagittarius, the B ones. All the remnant upstairs. There's a background galaxy in there. You got different threads. You got Sagittarius A right in the center there. And you got the C, what they call the snake, the mouse. These are the different ones that what they call them when they do the one of the center of our galaxy. Okay, Scott, the next.
That was the last slide.
Okay. Then. Okay. So what I want to do is tell you a little bit about that, because I am very interested in radio astronomy. And I've started collecting information and books and stuff like this on it. As you see, some of the main things is going to be your antenna. So for antennas, amateurs can use an old one like this, an old satellite TV. There's plans out there to where you can modify it. You have your LNA down in here, and you can modify it. And just to give you an idea, this is LNA out of a low noise amplifier out of another one I have. It's got 3 of them in it, 3 low noise amplifiers on it. But you can use that there, and there's plans on there to make what's called an itty bitty telescope, an IBT. You can measure the hydrogen line. You can see thermal information off the sun. You can get stuff off of Jupiter with it. Okay. Now, for a little bit more sophisticated one, I bought a kit. That's 2 of them in there, tabs there to build a. That's my antenna on there like that with it. Okay, let me put this back up here. And in that right there, you have, this is a center reflector reflected back into it. An arm for it. It's based on software-defined radio. It's got connectors, your SDR piece that you put in a computer, RTL stuff like this, and all types of other things there to put it all together. Down there also does you can do hydrogen lines on multiple, depending on what galaxy you want to do on there with that. They also have something that's called a radio Jove, which is measuring noise and different things off of Jupiter. There's a kit over here that I bought from it with some electronics and parts with a PC board, because I got it cheaper because I was electronic tech. I can build, I can solder and put my own board together right there rather than having to pay for it. Okay, and off that there you have a radio Jove receiver. This is the manual for it. And I've also gone into, and the great courses, they have a radio astronomy, with the manual goes with it here, radio astronomy course that you can learn a lot from. And I've been a member of SARA, the Society of Amateur Radio Astronomers. And through SARA, I got discs here about the itty bitty telescope and how to build them, their journals for 20, 30 years on one of these discs, and quite a bit of information from SARA on there. And then last, I'm so interested in stuff, I get antenna books. This is the Radio Relay League's antenna book for ham radios. And this one here is a antenna book here, just in the last year, it has been translated from German. As soon as it's available, I went ahead and got it, because I'm interested in all this. I study these things. Now, the other thing I want to say is that there is a radio astronomy observing program with the AM, of which a lot of this stuff here is necessary. There's 5 or 6 steps you have to do. You get a choice of some of them there. Some of them you do a choice of 1 or 2 things out of it. But 4 out of the 5, you have to build your own equipment.
I think it's
Yeah,
just
I
one out of the
kit.
5, actually.
What?
I think it's just 1 out of the 5. Some of them are just like very,
Well,
very
they might have
simple.
changed it because I printed this out a couple of years ago. But anyway, you do have to build some equipment on. That's part of the reason why I got some of these kits to build that. So anyway, we got that. And then there's that. Those are the actual instructions there. But this is all types of more information from Sarah on antenna basics and all types of stuff involved here. So if anyone's interested in it, we have all that there. So now, any other questions? Any questions? No? No questions?
I mean,
We
you
don't
talk
know
about,
enough to ask questions.
I mean, you talk about what data, you get, I think, for us, maybe talk about, what you're planning to, what kind of data, what things you'd like to be able to observe using this.
Usually what I have here is mostly going to be hydrogen lines. I think I can use that antenna there with a little bit different receiver information. You can, higher frequencies, you can get masers. You can get quite a few different things like that. I can measure pulsars and see quite a few different things like that can be done depending on the frequency you're doing it on. And it might require a different antenna. And I'm looking into how to build my own feed horns and what they call the CAN type. I've been doing research and study on that there, or the higher frequencies, because these only gonna do like around maybe up to 2.4 gigahertz. So all these, and for those, some of those you got to do 10.2 and even high up to 20.4 maybe gigahertz for some of the other things there. But this is actually, rather than just the optical and photo things like that, this is enables you to do more things and observe more of the deeper, shall we say, workings of the universe, shall we say, something like that.
I think you can actually use it to create a map of the Milky Way if you have enough time. You just
Yes.
let the Milky Way roll over the same thing overnight, and
Right.
over a couple of weeks, you get the data you need.
That's what you do. You do also, they do what they call a drift scan, which you just set up and leave it point there and just let it run. For 12, 24 hours, whatever like this, you let it run. And as the Earth moves around like this, you get the whole sky in a band like that there. But it's just one thing I'm interested in. And for whatever it's worth too, big radio telescope outside here, outside the building right here. I'm working with LSU right now. We're going to try to, I know we're going to get it. I was hoping to get it by Alcon, but I don't think we will. But I'm working with them because they've already agreed that they will help get it refurbished and get it back operational again. Now, that's a bigger dish, but it depends on what the LNA and electronics are as to what we're going to be able to do with it. That's to be determined. And the newest stuff on it there, to refurbish it, is going to be with a software-defined radio, which is on everything that's now going nowadays with software-defined radio rather than discrete stuff like that board would be. That's to be discrete.
You want to tell everybody what SDR is?
Yeah.
I'm familiar with it because I have an SDR. It's basically a USB dongle. You plug in.
Right there, it's USB in only in right there. You plug it in, and you can software can tell it what frequency you want to scan, what you see, anything else like this. And people, everything from AM, FM to airplanes to police and stuff to ships. You can get satellites. You just define, depending upon your antenna now. You define what frequency band you want to observe and or monitor. And this one little thing here can do it all, almost all frequencies. Up to a certain point, sometimes you have to get a different one for another set of frequencies off. But normally the most ones here, they'll cover almost every frequencies from low frequency, like 100, 200 hertz, all the way up to 10 to 20 gigahertz sometimes, depending on which one. That's a SDR, software-defined radio. Because you use the software to define what you want to observe.
You use hacking the service FM.
Yeah, I don't know about hacking, but you can pick up their signal, yes.
But I know that buckwheat, somewhere in the
Well, and there are ways to actually, so on the radio side of it, there are ways to actually handle the digital trunk system
Mhm.
and receive on there as well. So they have kits on Amazon. So if you want to, if you kind of like listening to a scanner or stuff like that, pick one of these up. $30, $50 for the kit.
Fairly simple.
Yeah. Now they do get warm.
Yep, they can. They
They
can
get
get,
warm.
in fact, they can get, in some cases, they can get hot enough to where you don't even want to hold it. Depending upon frequencies and different things like this, some of them can get warm like that, hot. But I'm in a lot of different Facebook groups and stuff and things like this for RTL SDRs, for amateur radio, for the SDR stuff, for amateur radio telescope stuff. I'm in a lot of these different groups. I'm always really studying on it and learning. So my problem right now has been getting time, because as you all probably know, I'm quite busy with different jobs and stuff that I do. So as soon as I get the time, I'm gonna start building this stuff, and I want to start monitoring it and work on that AL program. Yes, sir.
So I've noticed your 2 dishes you had there, they look to be a similar size. What are the other differences in between them?
Okay, the two right there is one. It's put together, the two pieces are put together. Okay, the one down here is like an old satellite TV dish.
Right.
Okay, that one here will probably be a little bit, I might be able to get a little bit more, a little bit different frequencies on it, while this one right here basically is like heat signatures out of Jupiter or the sun, and maybe you can get the hydrogen line off of that. That's all you're gonna be able to get off of that one there, but it's enough. That's sort of like the first step for sort of radio astronomy. You build one like this, it's easier to do. And by the way, a lot of people, they use their telescope stands for tracking. And you mount that on it, either one of them you mount and it'll track for you. A lot of people use a little stand that they have that they're not using anymore for the telescopes, for tracking purposes. Did that answer it for you or not? Okay. Any other questions here then?
What kinds of things are on the AL list? They have specific things you need to observe.
They have programs that basically they have some for observing meteors, they have some for observing the sun, some for observing the Milky Way, some for observing Jupiter. Basically, it's one of those pick and choose your own type thing. I think by the final stage, and they've got 3 or 4 different stages, or 2 or 3 different stages. The first one is just like 1 or 2, and then stage 2, you have to actually build some equipment, I think, and then by the time you get to the 3rd stage, you basically have to go out to a professional observatory and get some time.
You have to get the information from a professional one, but they give you the information that you can contact them, and that professional one will provide you the information you need to do the calculations and work in the program. That's the last step right there. But the whole thing is right here. It's about a year old, something like that, since the last time I said this was updated was in 2015, so it might be a newer one right now. But I have the whole program here if you want to look through it.
And it can be done during cloudy weather.
Yes.
Yeah, it's not that terrible.
Yeah,
of a
because
program.
radio waves aren't stopped by anything. Yes, sir.
Okay, good question. Since it's not the visual realm, how do you point? How do you figure out what you're looking at?
You probably use a program of some type, like we used to look for stars.
Self-organized where it's looking at kind of.
Yeah, there, and you try to line it up as best you can, something like that. Now, if you have a tracking scope tripod, you can put it in, like say you want to observe, say.
But you still have to align it the first time.
Well, you
Well, you have
just
to
do
do
it the
that
old-fashioned
physical,
way.
right?
Visual, you can look at it and tell.
Well, no, like for astrophotography, you got to do a pretty good polar alignment for it, like this.
Okay,
This is enough to where,
so you can pick a star and look at it as you're focusing and get it.
right, this is not as critical as astrophotography is.
Okay.
As long as you can set your stand up there like that, line it up, you can do visually with a compass, line it up as close as you can with north. And then if you know your right angulation declination on it, you move it over there like that there and use the tracking and keep it on it. Or as I say, you can do the trick. Radio waves is not that critical Because by the time they get to us for wherever it is, they've spread out so far. They're just
Okay,
so low in power. That's the thing. That's the major thing on it, the low power. It's like right now, our geosynchronous satellites at 22,000 miles up, I think, like that, like for satellite TV and stuff. They might be a 15 to 20 watt transmitter, and you have like 1/1,000,000th of a watt of power coming in and hitting your antenna here. That's why you got to have the LNAs, low noise amplifiers, they amplify it billions of times. That's why it's called low noise too, to try to keep as much noise as you can out of it. So the real thing on that is the power coming in like that and how well your low noise amplifier works on it. It's not that critical to line it up. And if you want to say, as I say, you want to stay on one particular object, like if you want to go to the Crab Nebula, which is a big nebula, you need a tracking stand, and you have to line up well enough there to where it could stay fairly close to it like that, and you just let it track across it. Because
yeah, once you line it up in the tracking stand, it'll keep you lining up. But-
if you want to do a specific, if you just want to do a drift scan, or if you just want to do the Milky Way, you don't have to really use the tracking. Okay. Any others? I guess that's about it then. Thank you very much, people, and I guess we want to end our live stream now.